morning to all of you. My name is Vishal Jayaswal. I am assistant professor in Department of Computer Science and Engineering, Ajay Kumar Garg Engineering College, Ghaziabad. Here I am going to take lecture on computer organization and architecture subjects, and the topic of this lecture is instruction format. In previous lecture, we will talk about the basic concepts of instruction formats and types of instruction format, and in this lecture we are going to cover the numerical example of the instruction format. Here we are taking an example for the instruction format, that is write a program to evaluate the arithmetic statement, and the statement is x equal to e minus b plus c into d into e minus f upon g plus h into k. This is the arithmetic expression for which we are going to create using a general register organ computer with 3 address instruction format, using a general register or computer with 2 address instruction format, and we also using an accumulator type computer with 1 address instruction, and last, that is using a stack organized computer with 0 address operation instructions. This is the questions for which we are going to write 3 address instruction format, 2 address, 1 address and 0 address. To solve this question, first we have write a whole expression, that is x equal to a minus b plus c into d into minus f divided by g plus h into k. For the solving this question, we have to simply in our mind, that is the BODMAS rule. With the help of BODMAS rule, we are going to solve this question. Here we can see that first if we apply the BODMAS rule, first we solve this bracket part. This bracket part, and for the solving this bracket, that is d into e minus f, and in this part we are going to solve this part. As I told in our previous lecture, in 3 address instruction format, we are going to use only 3 address for each instruction. Address may be or memory address, or address may be or register address. So for the solving this bracket, first we solve d into e, then we solve minus f. For d into e, first we write the instruction MUL, means multiply. We take R1 one register, in which we are going to multiply d into e and store the result in R1. So the explanation of this instruction is m of d multiplied by m of e, and the result goes in the R1 register. So in this way we are going to solve this d into e. Then we have to subtract from f. For this we write the instruction, that is sub, means subtraction, R1, that is holding the multiplication of d into e in the previous step, and R1 comma R1 minus R1 comma f. It means this is the explanation of this instruction is R1 tends to R1 minus m of f. In the previous step, we have calculated d into e and store the result in R1, and here we are going to subtract f from R1, means d into e minus f is solved and result is in R1 register. So our intermediate result is in R1. After solving this portion d into e minus f, we are going to solve this part. This part we are going to solve. For this, we have to multiply d into e minus f with the c. For this, we use multiply instruction, and R1 comma C comma R1. It means we are going to multiply C with the R content of R1, and in the content of R1 contains D into E minus F. So M, it means R1 tends to M of C multiplied by R1, and in the previous step we have the value of R1 is D into E minus F, that is multiplied by C, and that the result is stored in R1. It means the whole result, this whole result is in R1. After that we are going to solve subtract, means we are going to take another register, that is R2 and comma A comma B. It means we are going to subtract A minus B and store the result in R2 register. Here M of A minus M of B, and we are going to store the result in R2 register. Here we can see that the sign, that is subtract and add, these are the two signs. But if we talk about the plus and minus, the plus and minus priority is the same. The priority of the plus and minus sign is the same, but this is this hold the property of left to right associativity. Left to right associativity means first we traverse from the left. If we got the plus sign, so we perform the plus operation. If we got the minus sign, we perform the minus operation. Here in A minus B plus C, we got the minus sign, so first we subtract A minus B, then we add the C. So subtract R2 A comma B, it means M of A minus M of B, and stored this result into the R2 register. After that, this solve E minus B and it is in R2, and this whole result is in R1 register. After that we are going to add this, we are going to use this plus operation. For this we are using the add instruction, that is add R1 comma R2 comma R1, means we are going to add R2 plus R1 and storing the result in R1, means these contains in R2 register, sorry, R1 register. Means here before the division we have two portion, that is numerator and denominator, and the whole numerator is solved and stored in the R1. After that we are going to solve the denominator portion, then we are going to solve this portion. So for this we first solve H into K according to the BODMAS rule. So for this we use multiply operation, means mul instruction, MUL R2 comma H comma K. For this it means that M of H into M of K, these are multiplied and stored into the R2 register. So this is in R2. Then after we have to add this H into K into G. We have to add G plus R2. Then we perform this G plus H into K. For this we are going to use add instruction, add R2. We are taking one register, that is R2, G comma R2. G, it means that for this there is the explanation, that is R2 tends to M of G plus R2. Means the content of R2 register is added into the M of G and store the result in R2 register. So our denominator, whole denominator is in R2. Our numerator is in R1. Our denominator is in R2 register, and there is a one operation that is to be performed, that is division operation. For this we are going to use div instruction, that means div x comma R1 comma R2. It means we are going to divide R1 divided by R2 and store the result in X, because we can see that our whole result is stored in X. For this we are using X here. So div X comma R1 comma R2, it means R1 divided R2 and store this result in M of X, means memory location of X. In this way we are solving the 3 address instruction. You can see in 3 address instruction format, every instruction means every instruction having 3 address, not more than 3, not greater than 3. Every instruction having the 3 addresses. Addresses may be or register, addresses may be or memory. So second, we are going to talk about the 2 address instruction format for this particular arithmetic expression. Arithmetic expression is same, but this time we are going to use 2 address instruction format. It means that during the solving this problem, we are going to use only 2 address. Address may be your memory or address may be your register. So for this we are using we solve the question like 3 address instruction format. The sequence should be the same, but here we are using only 2 address per instruction. So for this, first if we see the arithmetic expression according to the BODMAS rule, first we solve this part. For solve this part, before that we have to solve D into E. And if we perform D into E, so we take D from the memory and come into the processor. So for this we use the move instruction. Move basically a data transfer instruction that are used to fetch the content from the memory to the register. So here we are using move instruction. Move R1 comma D. It means content of M of D means D is transferred to the R1 register, and register is in processor and memory location is in main memory. So M of D is transferred to the R1. Then after we have to multiply D into E. So we use multiply R1 comma E, means we have to multiply R1 into M of E and store the result in R1. So in this way we have to multiply D into E and the content is in R1. After that we have to subtract minus F. For this we are using subtract instruction. Subtract R1 comma F means we have to R1 tends to R1 minus M of F, means before this instruction R1 contains D into E, and R1 minus M of F means D into E minus F, that is performed, and store the result in R1. So this whole bracket result is in R1 register in this system. After that we have to multiply this content with C. For this we are using multiply operation, that is multiply instruction. Multiply R1 comma C, and it means that the explanation of multiply R1 comma C is R1 tends to R1 into M of C, means the content of C is multiplied with R1 register and thus store the result in R1, and it means that this whole content is in R1 register. After that we are going to solve this portion. For solving this portion we have to first fetch A from the memory, then perform the operation. So for fetching A, we use the move instruction. Move R2 comma A means M of A is fetched from the memory and going to the processor register, that is R2. After that, we have to use subtract because we have to perform A minus B. So here we are going to use subtract R2 comma B means R2 tends to R2 minus M of B. It means that is performed, that is A minus B, and the A minus B result is in R2 register. So this A minus B is in R2 and this portion is in R1 register. So we have to add the content of R2 and R1, then we solve the whole numerator part. For this, we are going to use add instruction because we have to add the content of R2 and R1. So we are going to use add instruction. So add R2 comma R1, and here we are using R2 as a destination and R2 as a source. So R2 tends to R2 plus R1. It means our whole numerator part is solved and the result is in R2 register. So this whole numerator is solved. This whole numerator is solved and the result is in R2 register. Our R1 register is free, so we can use R1 in solving for the denominator part. So here we can see that for in the denominator part we have G plus H into K. For solving G plus H into K, we solve this part, that is H into K, and for this first we move H from the memory and taken into the processor. So we are using move instruction for fetching H from the memory and taken into the processor. So move R1 comma H means we are fetching M of H and send to the R1 processor register. After that, we have to multiply H into K because we have to perform H into K. So here we are using multiply R1 comma K means it means R1 tends to R1 into M of K, and before this step R1 contains H. So we can see that H into K is performed and store is in R1 register. So our H into K performed and store is in R1 register. After that, we have to add G into the R1. So for this, you are using add instruction, that is add R1 comma G, and R1 comma G means R1 tends to R1 plus M of G. Here H into K is stored in R1 and it is added into the M of G means G plus H into K is performed and stored in R1. So we can see that our whole numerator is solved and stored in R2 register, and our whole denominator part is solved and stored in the R1 register. And here there is a divide sign, means we have to divide R2 by R1. So for this we are using div instruction. Div R2 comma R1 means we have that is R2 tends to R2 divided by R1, means our numerator and denominator part is divided and stored in the R2 register. So our whole right hand side part is in R2 register, and after that we have to move this part into the X memory location. For this we are using move X comma R2, means we have to send the content of R2 register into the memory location M of X. So in this way we have to write the two address instruction, in which we can see that in each instruction we are using only two addresses. First is opcode, and these are the addresses. And addresses may be or memory address or processor register address. So in this way we can write two address instruction for the particular expression. After this we can solve the same arithmetic expression with the help of one address instruction. So for writing one address instruction for this particular statement, same statement, but our writing style should be changed, because in this one address instruction we have to remember one point, that we don't use move, because in one address instruction we can also call one address instruction that is also called load store architecture. So in load store architecture we can use keyword load for storing, for fetching a word from memory, and if you talk about the store means we have to write a word into the memory. So here we are using load and store instead of move, as in two address instruction. So first we solve this expression according to the BODMAS. We have to solve this part first. For solving this part first, we have to move D from the memory to the processor. And one main important point in the one instruction format is we have only one register, that is called accumulator. In one address instruction we have not used any other register instead of accumulator, because we are having only one register in case of one address instruction, that is called accumulator, that is called AC. So one address, first we have to move D into the processor, and in processor there is a one register that is called accumulator. So load D, first we write instruction load D, means D is M of D is loaded into the accumulator, means accumulator register contains the value of D. After that we apply multiply E. Multiply E means that is AC tends to AC into M of E, means the content of E is multiplied with AC and store the result in AC. Basically multiply means this, and in this way we can see that D into E is solved and store into the AC. So after that, this is in AC. After that we have to subtract minus F. For this we are using subtract instruction, and subtract F means F is subtracted from the AC and store the result in AC. This is right in this way, AC tends to AC minus M of F. After that we have to multiply this part with C. So we are using multiply operation, opcode, and one address that is C are using here. So multiply C means C is multiplied with AC and the store the result in AC. So AC tends to AC into M of C. So we can see that this whole part is solved and stored in accumulator register. After that we have to solve this A minus B part, and for solving this A minus B part we have to store this intermediate result into the safest location. To store this intermediate result in safe location, first before solving A minus B, first we store this part into the temporary location, and here we are going to take temporary location T, in which we are going to store this intermediate result. So we write store instruction, and store T means we are going to store our intermediate result that is stored in AC and is transferred into the M of T, means in temporary location T we are going to store our intermediate result that is in AC. After that we are going to load A. Load A means we are going to take A from the memory and contains in AC. After that we are going to use subtract operation, means we are going to subtract B from the AC and store the result in AC, that is AC tends to AC minus M of B. After that we are going to add T, because this part is stored in T memory location and the current A minus B part is in AC, and we have to add AC plus T. So for this we are going to use add T, means we are going to add AC tends to AC plus M of T, means the whole numerator part is solved and is in AC. After that, because we are a limitation of register and we contains only one register, so for this first we store this whole numerator part in, that is in AC, in the safe memory location, and here we are using T location for storing the numerator part, that is store T. That means AC the content of AC is transferred to the main memory location T. After that we have to solve this part. That for this first we load H, because we have to first solve this part, after that we have to solve this part. So for this we have to first load H. Load H means M of H is transferred to the AC register. After that we have multiply K, means H into K, that is AC into M of K is multiplied and contain result is transferred to the AC register. After that we have to add G, means we have to add AC plus M of G and store the result in AC. After that load X. Load X means because here we are using AC plus M of G and store the result in AC, and we are going to use load X, means we are storing the result, store X, here we are using store X, means the whole denominator part is solved and stored in M of X. After that first we load T. Load T means first we the whole numerator part is in T, so first we load the T that is in the memory and transfer to the accumulator register. So load T means M of T is transferred to the AC. After that div X. Div X means the content of AC that are having the numerator part and divided by the M of X. M of X contains the denominator part. And finally we store the result in X. So for this we are using store instruction, that is store X, and it means the whole result that is in AC is transferred to the M of X. So in this way we are solving the one address instruction for the arithmetic expression using one address instruction format. In this we are using only one address. We cannot use more than one address, and we can see that in each instruction we are using only one address. So in our next lecture we are going to solve this expression with the help of zero address instruction format. Thank you for watching this lecture. Thank you.